First, thanks to PyData for hosting and allowing me to talk. It's been really great so far. So I'm talking about this package developed by Twitter. They call it Breakout detection. They developed it maybe 2014 by a group of people there. And it's a package that detects level shifts in time series data, or in general, univariate data. So this is a paper. These are the guys that wrote the algorithm behind it and implemented the package. So they originally wrote it in R, and then later somebody, I forget who, I believe it was Nicholas, ported it over to Python. I thought it was a pretty interesting package. It's kind of, the goal of this talk is to hopefully kind of walk through it a little bit, maybe save you guys a few hours later if you ever want to use it on your own. So, and I thought the math behind it was pretty fascinating. They kind of use pretty recent math, which is not always the case. So let's start off. What is a level shift? So a level shift in a time series is an abrupt, sustained change of trend level starting from some given initial time. So this is so I have an example of some fake data with a level shift. This is an inwards definition, and it's kind of one of those things you know it when you see it. I know a level shift when I see it, and part of the trouble is why this paper was so great. I think is it's up to people to define a good mathematical statistic that measures when a level shift happens. All right, so why do I care? You probably have, if you deal with time series, you might have reasons why level shifts are significant to you, but they can be indicative of a major event or a paradigm shift in what you're measuring in your time series. All right, so I have a few examples. So this is one of the things, kind of one of my pet peeves is when people write a great package but they give no examples. So I pulled a few examples of stock data, which level shifts, you can really see them, you can visualize them, and so why not? So this is S&P 500. The blue line is the open value of the S&P 500 from 2005 to 2010, and this black vertical line is where the algorithm detected a level shift happened. Okay, so middle of 2008. So that's we know what happened then, the red line is the moving median, so over past 90 days, I think. And so there's a reason why I chose moving median rather than moving average, and I'll try to explain that a little bit later. So next example, dot-com bubble, late 90s. So this is a graph of Yahoo stock from 97 to 2009. And I made such a wide tail to the right because I just think it's kind of fascinating to look at things like this. Over here, 2008, that's what we just saw. That's the economic recession, and the dot-com bubble was so much bigger. It's crazy. And again, this one, red is a moving median, and I just wanted to point out that the breakout, the level shift, isn't detected until that plateau on the red line ends. Okay, so the algorithm, the statistic that they define is more related to to a change in median than a change in mean. All right. Next example, Netflix. From mid-2012, mid-2013, Netflix started producing TV shows, starting with House of Cards on February 1st. So their stock jumped. And Chipotle, over about the past year, their stock took a little dip because of some E. coli found in their food. So, okay, so that's it for examples. Just I think this just see how this performs a little bit. That's the breakout detection package, and it actually performs pretty well compared to a lot of other level shift detectors and in general anomaly detectors or outlier detectors, not anomaly. So a lot of outlier detectors are implemented in R, and they're starting to be kind of ported over to Python. But I think this one is performant. I'm not going to compare them up here. There's some papers written in that paper I showed you. They compare a few of them. Okay, so next, what is this used for? So at C2FO, the company I work for, if you were here earlier this morning, see Piero's talk, he showed that we have tons of time series data. So we have on the order of 100K time series, a few hundred thousand, and we in our system, in our business, an event occurs. For those people who weren't here, I'll try not to talk about too much of the specifics. I'll kind of abstract it. So an event occurs, possibly creating a level shift in some of these time series. And for us, we want to know, did that event actually create a level shift in some of these time series? Which one? If so, which ones? And so we want an algorithm to go through all these hundreds of thousands and pick it out. So this is an image that Piero had in his talk. So this is an example of what some of our time series might look like, and this is one that has a little bump, a level shift. So the event that I'm referring to is, if you're there, the event is a new buyer coming into our system, and this company was doing business with that buyer, and we didn't see that until the buyer came into our system. So we have more information about this company. So this buyer coming into our system happened here, and so we can know beforehand like which companies do business with which buyers that come into our system, but we don't know exactly how it's going to affect the time series until it happens, and so we want really to have some way of evaluating that. So that's kind of how we use it at C2FO. All right. And in general, kind of exploratory analysis or impact analysis. So for example, the examples I showed you of the stocks, I kind of, how I came up with them is I looked through, the S&P 500 stocks, pulled them, ran the breakout detection, saw like, do they have interesting breakouts? And then when it detected one, I saw, I kind of explored and I said, oh, was there something interesting that happened there? So it can be, a flag to say, oh, something interesting might have happened here. Okay. All right, so, I figured I'd say something about installation. So you can go to this this guy's GitHub. He was the guy, I believe he was the guy who ported it over, maybe not. And these instructions are on his GitHub, but if you're just looking at this later, they're right here. So clone the repository, install this. All right. So I have a few examples in Jupyter here. This one. See that okay? All right, so first, so here's a code that I use to generate those graphs like that. So I have some imports. So once you've, and I'm using Panda's wrapper for the Yahoo Finance API. And once you've installed breakout detection, Now you import it, you just import breakout detection like that. And so here get the data that I want. So this is getting S&P 500 data. And one catch that is not totally obvious in the documentation is that you have to scale your data between 0 and 1. So that's, I didn't really realize that until I kind of dug into the source code where they say, make sure your data is scaled between 0 and 1. So this is, this scales it, make sure I'm not dividing by 0, so I take max of max. So if the highest value of my data is less than 1, I don't want to bother scaling. And so here's how I use the package. So it's kind of like the calling fit in scikit-learn. So breakout detection is kind of it's kind of an empty object, and so you call it here. You specify which one you want. So EDMX is the standard one. They have a few versions, but EDMX is the standard one. And then when you call evaluate Z, Z was the scaled data of the time series. Evaluate Z finds a breakout detection and stores it in a value, or sorry, in an object, a property of EDMX. And they call it getLoc. So for get locations of the time of the breakout. Okay, so then you plot it. I plotted it. You find the locations, and I plot a vertical line on the breakout detection or breakout points. All right, and so they do have another algorithm implemented where you can detect multiple breakout detections in time series, and the similar way of using it, except it's called EDM multi. So EDM multi here, I'll detect multiple breakouts, and in the evaluate function, you have two parameters they have to worry about: beta and degree. Degree I wouldn't worry about unless you really want to dig into what it is about. But basically, beta and degree combine to form a penalization function. So basically, how hard is it to tell to allow the program to say a breakout was detected here? So basically, they compute a value at each point, and if the value is large enough, it flags it as a level shift. Okay, so larger beta corresponds to harder to have a breakout. So we can change it here. I'm still connected, yeah. 0.8. Only detect one, which I know it's kind of weird that it's right here, but I don't know. So I really wish it was around 2008, but I don't. I think I have an idea of why it's detecting over here, but we don't need to go into that right now. And then so if you change it to something less than 0.3 or 0.003, it'll detect a few more. Okay, so it detected one more. Okay, great. So that's basically how you use it. Beta, higher beta, it penalizes more, makes it harder to find, to flag something as breakout. Lower beta makes it easier. And degree is kind of the degree of the polynomial that is the can't think of the words, but the penalization factor. So there's three values for degree that it can take on, 0, 1, or 2. 0 negates the penalization. 1 is basically constant, and 2 is a linear scale. So okay, so that's a multi. The code behind these graphs. So let's. All right, so now is my super condensed explanation of the math that's going on behind the algorithm. And then the next slide will go through the algorithm. All right, so the paper that they wrote, I showed a snapshot of the paper at the very beginning. It's actually pretty interesting. They use some math that's developed pretty recently. And they combine two different things. One of them is called energy statistics. And a big thing in energy statistics is called the energy distance. All right. So this is the energy distance. This calligraphic E of x, y is this formula, expected value of x minus y minus this. And so I'm not defining anything up here. So I'll just say out loud what these things are. So x prime is so I said x and y are independent random variables. X prime is another random variable that comes from the same probability distribution as x, but is independent from x. So if that doesn't mean anything to you, x prime is kind of same but different than x. So I can give an example actually. So the kind of canonical example in explaining this is, if you have a coin that you flip, a fair coin, it has probability distribution of half landing on heads, half landing on tails. So that's the probability distribution of that event of flipping a coin. The random variable, x, associated to that coin is, you typically say, 1 if it lands on heads, 0 if it lands on tails. So x prime, for example, could be the independent random variable associated to flipping a different coin. So same probability distribution, assuming the coin is fair. So the two coins have the same probabilities of landing on heads and tails, but the events of flipping the two coins are independent. So that's a relation of x to x prime, and then similarly y to y prime. Okay, so then these xi's are random samples of the random variable x, or just samples of the random variable x, and the yi's are samples of the random variable y. So we can approximate this energy distance with this formula. Okay, so replacing the integrals and the expectation values with sums, finite sums. And so there's a reason why why energy comes up in there, but I'm not going to go into that, mostly because I don't totally understand it. But basically, there are some equations that show up that look like equations that govern energy in classical mechanics. So, all right. So the next thing this combines is something called robust statistics, and so it's actually a field of statistics. It's not just I would like my statistics to be robust. There's a field of statistics that they try to formalize this idea of making robust statistics rather than non-robust. And the slogan I've always heard with this is replace the mean with the median. So mean is a non-robust statistic. If you add on another, if you have a collection of numbers and you take the mean and then you add on another number that's a lot bigger than any of the others, the mean will change significantly. But the median, however, typically does not. So replace the mean with the median, and that's kind of the slogan for this field of stats, but that's not like everything that they do. But that is kind of what we're going to do here. We are going to replace the mean with median, and well, we are going to get this robust version of the energy distance approximation. And so the word distance is in there because it is supposed to be thought of as a distance between the two random variables. Okay, so kind of usual way you think of distance, bigger number means they're further apart. Smaller number means they're closer together. Okay, so this E tilde of xy is our new robust version of energy distance between random variables. All right, so now that we have all that, the algorithm is fairly short. If you have your time series, z1 through zn, we just iterate through the time series, and we split it, iterate I over 1 through n minus 1, and we split z into different segments, x, I, and yi, and those are our different random variables. And we plug those into that robust energy distance, and we calculate that for every split, and then we find the maximum energy distance. So the algorithm actually returns the index of the point with the maximum energy distance. So saying if we split our time series at a certain point, when is the distance between those random variables the largest? And so that's the idea. That's and that's kind of going back to the median. That's why I graphed the rolling median rather than rolling mean. So that's it. Thank you.
Did you observe where the algorithm identified breakout so that you didn't see that there really was a breakout?
Oh yeah. So he asked about if there were times where I observed breakout, the package detecting breakouts where there were none, and yes. I mean, it was never at a time where it was completely flat. There was always something kind of strange going on. But for instance, in the multi EDM multi, you can set the beta, the penalization really low, and it'll detect many breakouts everywhere. But yeah, it does. But generally, it doesn't. So, yep.
How much data do you need before a breakout can be detected?
So in the EDMX, very minimal data. I believe they do have a buffer, but it's pretty small. I can't remember the default, but they do require a buffer kind of at the beginning of your data. And then in the EDM multi, you can also set a buffer, so that will kind of act as a crude periodicity. Can't think of the word, but kind of a crude periodicity like a factor. So if you don't want to detect breakouts too close to another, you can set this buffer parameter. I believe they call it max size in the thing. So, yep.
So what's the advantage of using energy distance instead of another metric like KL divergence?
Well, so I mean, I don't know the other way you use tail distance, but one thing that this is, why this is advantageous is because of what I was kind of hand waving and saying, medians are more robust than means. This does perform better when your time series has lots of kind of spikes and other noise. So they do have some good examples, or they have one good example where there's kind of some spikes in the time series, and it detects level shift even though there's kind of a lot of noise going on. And so, which is something that I kind of a shortfalling of some of the other packages that I've observed, like maybe think change points and TS outliers, they tend to detect level shifts at points that are just kind of spikes. So yeah, so one of the main advantages of this is that it's a little less sensitive to noise, so it can still try to find that level shift.
How robust is it to seasonality generally? I know you didn't adjust for seasonality, but
Um, so you asked how robust is it against seasonality? And I, so can I don't know if I totally understand the question. Like,
So if you have a time series that has a very
mm,
distinct seasonal pattern,
okay.
do you need to extract that seasonal pattern before you run the breakout detection, or does it actually not make a difference?
Uh, yes, you do have to. Well, so if you know that seasonality, you can um, put in. There is a parameter in the EDM multi for, well, yeah, I just said, I guess, but that does act as kind of a seasonality component so that it will say, don't detect a breakout detection for another, whatever you specify. And, typically it's a good idea. So if you are dealing with data that's on the scale of years, maybe you want to put in, and you have maybe you have a data point for each week. Maybe you want to put in 13 for each quarter. But yeah, so the EDM multi does have some capacity for dealing with seasonality. Yeah.
Is there any standard approach for thinking about how you set that kind of degree parameter within EDM multi?
Oh, I mean the beta, or
Yeah.
yeah, okay. Not not really that I've seen. I think I kind of use it as an exploratory thing. Maybe there's a more sophisticated way to go about it. But oh, sorry, I'm not repeating questions. So he asked about basically how do you know what to set beta to, and you know, I kind of to be honest, I kind of play around with it a little bit. Like I said, we have a large number of time series, and so I look and see. I get a beta that kind of works for a few. I take a few, and our time series are pretty similar in nature. So if I find a good beta, then I'm fairly confident that it'll be okay for the other ones. Oh, yep.
Do you use like an ensemble of other methods along with this one to detect anomalies, or do you
Um,
mostly rely on this?
for now, really, for detecting level shifts, so this is kind of the main one. I evaluated some other ones, and this was the most performant for our needs. One bad thing is this is very specialized. There's other packages that detect level shifts, whatever additive outliers, innovative outliers, whatever they're called. So this is very specialized to just level shifts. So yeah.
How sensitive is this algorithm to non-uniform sampling in your time series? So if you had like a gap between your sensors and down or something like that, how much less robust might your results be?
So asking about how robust is it against non-uniform data, and so maybe if you have a gap in our data. So I'm not sure. So are you assuming your gap is filled with maybe zeros, or do you just fill in the gap and kind of glue them together? Or
Let's say going.
I mean, I think then it would most likely detect a breakout. There, it would see there's a dip there. So I don't know. Yeah, so I would assume it would detect a level shift, where there's some missing data because there's a sharp drop there. But um, yeah.
So two questions. One is related to that. How good is it if you have a heteroscedastic time series, as in like the volatility so like changes over time? Does that probably impact your view on whether the level shift has occurred or not? And then the second question is, so like as you look at like the recent examples, like does it, so like how much
So the first question was on if there's a significant change in volatility over time in a time series, does that have an effect on the algorithm? And not really that I've seen, and I don't know. I don't know why. I don't think it should. So from what I understand, I think it should be fairly consistent on, if you're, if you do have some change in variance or volatility over time, then I haven't seen really much difference, and it still performs fairly well. And from what I understand, that's kind of not what it's detecting. So I think it should do okay. So, and the second question was, sorry, what was the second question?
The whole lookup ahead bias thing, whether it sort of changes, whether you get raised
Oh,
as you
right.
get more data.
So, so, right. So he was asking if the algorithm kind of changes as you get more data, and so as far as the like EDMX, the one that just detects one, it'll detect the greatest one, the largest one. So if you get more data and there's there's a much larger level shift, it'll prefer that one over another one that was smaller. And the EDMX, or sorry, the EDM multi, it will it doesn't, if you have another big one that comes along later on, it should still detect the earlier ones. It doesn't really change those. Well, maybe I should be careful there, but unless you have unless you specified like a seasonality component and said, I don't want another level shift within a certain time, and then it'll kind of bump the smaller one. But, yep. Uh, so he's asking what does this do on spikes, and yeah, it'll ignore it. So it won't detect that as two level shifts or one level shift. So okay, thank you again.